Hello, and thanks for listening in. In this video, we will use vacuum gauge electrodynamics to develop a theory of the classical electron as a tiny orifice in a four-dimensional medium embedded in Minkowski space. Terminology is generously borrowed from continuum mechanics to develop a highly specialized vacuum Lagrangian. The vacuum Lagrangian leads to Coulomb fields which radiate from the particle at light speed. So, why does theoretical physics need radiating Coulomb fields and the vacuum gauge electron? First of all, it's well known that the classical theory of the electron is a disgrace to the field of physics and provides a very tragic ending to Jackson's classical electrodynamics. Second, experimental data are indicating a universe with unexplainable forms of dark energy and dark matter. Third, the Lagrangian formulation of the vacuum gauge electron, which we are about to discuss, solves all the fundamental difficulties associated with the classical electron. And finally, and most simply, vacuum gauge electrodynamics requires it. To begin, let's write the covariant vacuum gauge condition, which is a first-order differential equation for the potentials. The most significant solution to this equation is given by the vacuum gauge null potentials shown here, and it's important to mention that the radial property of these potentials is indicative of their ability to accurately describe the physics of a single charged particle. Now, if you work with vacuum gauge potentials long enough, you will be forced to introduce the classical electron radius and at the same time reinterpret the velocity fields of a charged particle as carriers of momentum flux. These momentum flux fields must radiate at the speed of light and are easily calculated simply by multiplying the particle's velocity fields by a fundamental constant surface charge density. Of course, this is an overt violation of energy conservation, which will certainly have serious implications for cosmology. At the same time, though, we cannot ignore the existence of the vacuum gauge condition. Finally, we note that the Poynting vector for a charged particle does not depend on whether the Coulomb fields are in motion or not, and can be written specifically in terms of the flux fields. Now let's talk about vacuum displacement. And for clarity, we will work in the plus triple minus metric signature. In addition, our flat metric tensor will be labeled by the letter G as in Jackson. Now let's write down our vacuum gauge potentials and remove a factor of 4 pi times sigma sub e. This defines a purely geometrical 4 vector, which will be referred to as a vacuum displacement vector. The vacuum displacement vector represents a deformation of a medium that we will call the vacuum. Essentially, this vector has pushed some of the vacuum out of the way, out to the classical electron radius r sub e, and has therefore created a void in the medium. It's important to mention here that we are not deforming space-time as in Einstein's general relativity. Instead, we are deforming a four-dimensional medium sitting in space-time, similar to deforming a three-dimensional solid sitting on a tabletop. Next, let's calculate the forward divergence of the displacement vector to determine a scalar field called vacuum dilatation. Specifically, vacuum dilatation is a measure of the amount by which the surrounding vacuum is deformed by the presence of the electron. In the rest frame, the dilatation is purely spacelike, but receives both timelike and spacelike contributions in the moving frame. An educated physicist will be aware that the terms vacuum dilatation and vacuum displacement have their origins in the three-space theory of elastic media. For comparison, we show the four-space and three-space calculations of dilatation. According to these formulas, both are derived from differential operations on a scalar field. In the four-space theory, this differential operator is the wave operator. To summarize, the three divergence of the displacement in the three-space theory measures a change in three volume. Likewise, the four divergence of the vacuum displacement measures a change in four volume. Continuing the analogy with the theory of elastic media, now let's define two second-rank tensors. Let eta mu nu represent a vacuum strain tensor, and let delta mu nu represent the associated vacuum stress tensor. we see that vacuum stress tensor is multiplied by a force constant mu sub e equal to 4 pi times the square of the fundamental surface charge density. In addition, this force constant is exactly the outward pressure of the classical electron charge density tending to explode the particle. Finally, the presence of the metric tensor indicates that our vacuum stress tensor is endowed with both restoring and admissibility properties. Since we know the specific form of the vacuum dilatation vector, this means we can calculate explicit forms of the vacuum stress and strain tensors. These explicit forms are shown here, and it's important to mention that neither one is symmetric. Instead, both have a single asymmetric term shown by the red arrows. However, the asymmetric term can be used to recapture the field strength tensor from either the stress or the strain tensor by forming the antisymmetric combination as shown here. With the previous definitions, we are now well poised to derive the Lagrangian for the vacuum gauge electron. Begin by writing the well-known electromagnetic Lagrangian. Now we can replace the field strength tensor with our definitions of vacuum stress and strain. Putting terms together, we arrive at a vacuum Lagrangian and also a null Lagrangian. In both Lagrangians, we take the field variable to be the vacuum strain. In addition, for consistency, we require the redefinition of the point charge density from the electromagnetic theory to be replaced by a new point force density, F nu sub e, in the interaction term. Now let's calculate equations of motion from both Lagrangians. The null Lagrangian leads to a divergence operation on the second index and produces no equations of motion. This justifies the name null Lagrangian. The vacuum Lagrangian, on the other hand, leads to a divergence operation on the first index. This gives us a new set of Maxwell-like equations based on the vacuum stress tensor instead of the field strength tensor. Nevertheless, the equations of motion are just the same old Maxwell's equations for the velocity fields of the electron, except now the fields themselves have become vacuum radiation fields, moving away at the speed of light. In addition, as we mentioned, the sources have become point force densities. Particle accelerations are still possible in the vacuum gauge, but they are calculated from a somewhat different perspective. First, let's define the perpendicular component of the acceleration 4 vector. We call it perpendicular because a contraction with either the retardation null vector or the space-like unit vector gives a value of 0. Now let's define an acceleration strain tensor that we will call epsilon mu nu. This tensor is a bilinear combination of the vacuum displacement and the perpendicular acceleration 4 vector. It's also a unitless quantity which allows us to add it directly to the velocity strain. Note, however, that vacuum dilatation determined by a contraction of indices on zeta mu nu does not change. In other words, the acceleration strain on the vacuum does not contribute to vacuum dilatation. We can write momentum flux acceleration fields similar to the velocity theory by forming combinations of the vacuum displacement and components of the perpendicular acceleration vector. Just like the velocity fields, momentum flux acceleration fields satisfy their own set of Maxwell-Lorentz equations. In addition, the source for the acceleration fields is still a force density. To be clear, the momentum flux we are showing here is associated with the acceleration fields themselves in the form of shear vacuum stresses. This is not the same as momentum associated with emitted photons. If we want to consider photon momentum, we look to the Poynting vector. We can expand this formula as a sum of 4 terms, and only the final term, which we show here, describes momentum associated with photons, and necessarily perpendicular to the flux fields. Now let's show one more formula, indicating how to obtain the conventional acceleration fields from the acceleration strain tensor. To summarize, we are compelled to give an official definition for the vacuum based on the close analogy with the theory of elastic media. So, vacuum, a self-generating deformable medium embedded in Minkowski space-time and characterized by both restoring and admissibility force constants having equal magnitudes. Of course, our theory represents a radical shift from the current theory of the classical electron. For it to be successful, we need to be able to quantize the classical particle and derive the theory of a Dirac particle. We also need to show that a radiating Coulomb field does not produce substantial changes to the structure of space-time, either locally or on cosmic scales. Thanks for listening in. We hope you've enjoyed this short video and have a great day.